This is section 6.3, our second to last section. We're going to talk about second order differential equations, and we are going to jump right back into forced harmonic oscillators, which I feel like we've been talking about this entire quarter. Well, they haven't always been forced, they haven't always been damped. But yeah, this is the forced harmonic operator that we always talk about. There's some mass here, but we divided everything by the mass to standardize it. And P is the damping divided by the mass. Q is the spring constant divided by the mass. And here is some forcing function, again, divided by the mass. So we normalized it in a sense. And we're going to use Laplace transforms to be able to solve new types of forced harmonic oscillators. There will be new forcing functions. Most of the interesting ones, for me at least, are going to be the discontinuous forcing functions. And the coolest ones we talk about in the next section. So we got some really cool situations coming up with impulse forcing in the next section. But for now, we're going to be solving these, seeing what these solutions look like with our Laplace transform. But before we do that, we're going to need some new Laplace transform formulas, and we're going to see some really cool ways of getting that. So the takeaway from this video really is not so much how to solve a problem, because you'll have access to what the Laplace transform of sine and cosine is. But this video is extremely cool for showing mathematical creativity and problem solving. We're going to talk a lot about different ways of approaching problems and really thinking about math from a new angle. And I think that's really, really exciting to me. So you're going to see some techniques that you probably haven't seen before. And it should be really exciting. All right, I get very excited doing this. So we're going to start by, I want you to find the Laplace transform of sine of omega t. Right? If we're solving differential equations, if we're solving harmonic oscillators, we're probably going to need to take the Laplace transform of sine and cosine. So we're going to come up with a formula, and there's a few ways that we could do this. Right? We could do it directly. All right? We know that the Laplace transform of this is going to be the integral from 0 to infinity of sine of omega t times e to the negative, e to the negative st dt. I forgot my notation. Yeah, so we're integrating with respect to t. We're seeing how close it is to e to the st. And that is going to be different for different values of s's. This is going to be a function of s. All right, I didn't write this down. So wanting to make sure that I got my notation right real quick. We could find this directly because we know how to find this integral. We know a few different ways of finding this integral. One of the ways that we could find this integral is we could use integration by parts twice. You've all done with an indefinite integral and an improper integral. You've solved these problems before in Calc 2. Integration by parts twice, you get things to move over and cancel. It's pretty fun. It's a bit of a headache. Or you could use complex exponents, right? We know sine of omega t is the imaginary part of e to the I omega t. So we could do that as well. We did that a lot in previous sections where we would complexify differential equations, use that fact that sine is the imaginary part, cosine is the real part, and we could do that. This is going to have partial fractions in it, and specifically it's going to have partial fractions with complex numbers. So this is a very fun way to derive this. Or this is what we're going to do. Let's use a different color because this is what's really exciting. We could use an initial value problem. What do I mean by that? I'm going to show you, but this is a very cool way of finding the Laplace transform of sine of omega t. So what we're going to use, we're going to choose this one. That's what we want to do because it's going to be the easiest. There's going to be no calculus. Well, we have to set up a differential equation, but we don't have to solve a differential equation. We don't have to take any integrals. We actually don't have to look at this at all. So what we're going to do is we're going to make an initial value problem with sine of omega t as a solution. That's what we're going to do. And then we'll just take the Laplace transform of both sides and solve for what we want. Okay, so how do we do that? Well, we know sine of omega t is going to be a solution to an undamped harmonic oscillator. So it's going to look something like, and leave some blanks here, y double dot plus something times y is going to equal something, and we'll need the initial condition to be something for both. Now, what does it need to be? Well, remember, this over here is what determines the natural frequency. We want the natural period to be 2 pi over omega. So what does this have to be? Well, we want S to be plus or minus omega times I, right? Because that's going to give us a sine of omega t. This is what we want. How do we get that? Oh, to get that, we just add omega squared to both sides, right? So that's what we wanted, so we just made it happen. And then what does the right-hand side have to be? Well, we don't really want a forcing function at all, right? Because we just want the natural response, because we want this as the solution. So our right-hand side is just going to be 0. What should the initial conditions be? Well, so far, what do we know? So far, what we have is we have that our homogeneous solution, which is our general solution, is going to be k1 cosine omega t plus k2 sine of omega t. So we want to choose these initial conditions so that so we want this to be 1. We want this to be 0, right? Because this is what we're trying to get as our solution. So we're creating an initial value problem to do it. This is a great exercise. This could be a good test problem, actually. All right. And with that being said, maybe it's a good time to pause the video. Now, what are our initial conditions going to have to be? Well, and we're going backwards, right? Because we want the left-hand side to be sine of omega t. Anyway, if we plug in 0, this becomes 0. And we get k cosine of omega t. We don't want a cosine. So we plug in 0, we want this to be 0. We need the initial condition to be 0. But the derivative, all right, we're going to need that. It's going to be y prime of t is negative k1 sine of omega t times omega plus k2 omega cosine of omega t. And we plug in 0 here. This part doesn't matter. All right, so we wanted k1 to be 1. Oh, wait, hold on. We wanted k2 to be 1. Great. And that'll be true when the initial value of the derivative is omega. All right. So we created an initial value problem with sine of omega t as a solution. Now we're going to use that to find the Laplace transform of sine of omega t. So y of t equals sine of omega t is a solution to this. Or is the solution, right? There's only one solution. We have uniqueness. Let's take the Laplace transform of both sides. What are we going to get? We're going to get the Laplace transform of y double dot, which we have not talked about before, by the way, plus, because we're doing it to both sides, but it's linear. So remember that technically we're taking the Laplace transform of this. But because it's linear, the constants come out in front. We can separate things. Omega squared times the Laplace transform of y, which I must say, this is exactly what we want to know. We know y is sine of omega t. This is what we want. And that's going to equal the Laplace transform of 0. Let's start with the right-hand side because that's easier. And then we'll deal with that left-hand side. What's a Laplace transform of 0? I have a guess, but remember Laplace transform is going to be integral 0 to infinity of the function times e to the negative st dt. Well, I know what that is. We'd set it up as a limit, and it's going to be 0 everywhere, so the limit will also be 0. The right-hand side is just 0. Okay. Then the left-hand side, what is that? So this is where we're going to use those properties that we talked about earlier. We know that the Laplace transform of the derivative of a function is s times the Laplace transform of its function minus its initial condition. So we're just going to say that, well, remember y double dot is just the derivative with respect to time of y dot. So we're just going to apply this property to the function y dot. So this part right here, the L of y double dot, that is just going to be the derivative of y dot. So using the property, that's going to be s times L of y dot minus the initial condition of the inside function, which is y dot. Again, I'm kind of mixing notation a little bit here with the dots and the primes, but I really shouldn't be. Y dot of 0. This should be, oh no, I copied it. Don't look, nothing's here. So that's the Laplace transform of the second derivative. And there's still plus omega squared. Remember, we're not trying to evaluate this L of y because that's exactly what we're trying to find. We don't know. That's what we're doing. Okay. And then we'll use that property again for derivatives. This is going to be s times the Laplace transform of y minus the initial condition. We're still subtracting the y dot of 0. Well, what is y dot of 0? It's omega. Plus omega squared, L of y. And we're actually almost done. Distribute that s, we get s squared, L of y, minus s times y of 0, which is 0. So it's just minus a 0, minus omega plus omega squared, L of y. And we have the left-hand side equals the right-hand side, so this is all equal to 0. What are we trying to find? We're trying to find the Laplace transform of sine of omega t, which is L of y, since y is the solution to this initial value problem. So it's a pretty cool solution, right? Just using properties of Laplace transforms. So we're going to add an omega over, and then factor things out so we get L of y by itself. We're left with s squared plus omega squared. And we find that the Laplace transform of y, and again, remember y is equal to sine of omega t. So we just found that the Laplace transform of sine of omega t is equal to omega divided by s squared plus omega squared. Ta-da! No integration by parts, no partial fractions, no complex exponentials, no complex numbers at all. Just creative problem solving. All we had to do is create an initial value problem in a careful, creative way, and we get it. And of course, this will be on your sheet. You can see the Laplace transform of sine of omega t is exactly what we found. And that's pretty cool, right? Like, that's exciting. Like, when I first read this derivation, I was like, I would not have thought to do that. But like, looking at all those creative ways of solving a problem is like one of the things that I love about math, right? We had 3 options. There were more options. We named 3 options and found a really cool solution for this. But we're not done yet, because I want you to also find the Laplace transform, and this one will be quick, the Laplace transform of cosine of omega t. Now you could use integration by parts, you could use partial fractions and complex exponents, you could use the exact same method we did before and create an initial value problem that has this as a solution. Or there's a 4th way that we could do this using what we just found out. Because what's the relationship between sine and cosine? You could use the cofunction identity, or you could use derivatives. I don't know if the cofunction identity is going to lead anywhere nice. But notice that cosine of omega t is the derivative of sine, right? That's just the derivative of sine of omega t, almost. All right, the derivative of sine is going to have us multiply by a omega. So if we really want these to be the same, this is what we'll need. This is true, right? Take the derivative of sine divided by omega, and that's cosine. So watch this. The Laplace transform of cosine of omega t is equal to the Laplace transform of 1 over omega times the derivative of sine of omega t. Oh. And now we're good to go because we know how to deal with all these things. It's a linear operator. The 1 over omega comes out in front. How do we take the Laplace transform of a function? Or of the derivative of a function? It's going to be s times the Laplace transform of the original function, which we just found, by the way, minus the initial condition. So can we factor this out and are just using this? What's the initial value of sine of omega t? It's 0. So we just have s over omega times the Laplace transform of sine of omega t, which is this, omega over s squared plus omega squared. We get some nice cancellations, and we just have shown that the Laplace transform of cosine of omega t is equal to s. So very similar, it's just with an s in the numerator instead of an omega. S squared plus omega squared. And let's check our work. Is that what our sheet has? Look at that. Look how easy that was. Just saying that Laplace transforms treat derivatives so nicely. Laplace transforms of derivatives are no problem. So we know the cosine is just kind of the derivative of sine. And we found it for cosine using what we found before. And that's pretty cool. That's one of the things I really, really love about math is like mathematicians are always finding creative ways of doing less work, which I can get behind. I am the sort of guy to spend 5 hours of work to do 1 hour less of work. I love it. So anyway, this is cool. Again, what do you need to know? You mostly just need to know how to use these, which we're going to do in the future videos. But I want to amaze you. I want to get you excited about math. And I want you to see where some of this comes from and be familiar with some of the techniques so that as you're solving problems, you can apply some of that creative problem solving if you're solving some problems that haven't already been solved. Okay? So trying to teach some of that like logic. It's cool. We do more practice of solving problems in the next couple videos. Bye-bye.